Research Results presentation. This is Victoria Beal with the Ohio LTAP Center. And a couple of quick housekeeping items before I turn this over to our presenters. First off, we are attempting to record the webinar, but please don't let that dissuade you from asking any and all questions you have. Questions can be asked through the question box in the GoToWebinar panel at any time during the presentation. The presenters will be periodically stopping, so I can read questions to them for responses, and then we'll obviously, answer as many questions as we can at the end until we reach our time limit. As I mentioned, we're trying to record. If the recording is successful, you will receive a link to the recording once we post it to our YouTube channel. But if it isn't successful, it's a good thing you're here, because you'll actually be able to hear things live and pretty much in virtual person, I guess. There are a couple of handouts in the handout section of the GoToWebinar box. If you haven't downloaded them already, you can grab the fact sheet for this project there, and also a copy of today's slides. If your system will not allow you to download those, we will send a follow-up email with links to those documents. So with that, I'm going to turn things over to our presenters. Rachel and Matthew, are you ready?
Yep.
Thanks.
All right, thank you so much, Victoria. My name is Rachel Cross. I'm an associate professor at the University of Cincinnati in the structural engineering area. And I have with me today my colleague, Dr. Matthew Steiner, also associate professor in the mechanical engineering and materials engineering, also at UC. We are two of the PIs on this project, which is the identification of maintenance practices to impede corrosion impacts on pre-stressed concrete box beam bridges. Just as a quick introduction, this was part of an ODOT OREAL 2 project that took place from September 2021 to September 2025. The report for this project has not yet been posted, but it will be posted. It should be posted shortly. The members of the technical committee here are a number of individuals, a lot of county engineers from all around Ohio, as well as a couple of members of at the main ODOT site, and then Vicki was our program manager. So thanks to these folks for their input and their passion towards this topic. So we're talking here about pre-stressed concrete box beam bridges. These are frequently used in short span county bridges as short span county bridges. They're box shapes with both the deck and the structural member contained within one section. Load is transferred between the adjacent beams through internal shear keys. It could have a composite concrete deck or a non-composite asphalt deck. We're worried here about the corrosion aspects, and so as you know, we use de-icing chemicals that would be placed on the surface during wintertime. Those wash off and can make their way into the joints and around the concrete and make their way in and cause corrosion. And so we're worried about that water getting in, those chlorides getting in, creating corrosion of steel, which causes the steel to expand and can create a variety of cracks that further aggravate the issue. We've seen issues of box beams having problems with corrosion, and these are the extreme examples that I'm going to show you that are luckily not very common, but this was a collapse that occurred in 2005, Lakeview Drive Bridge in Pennsylvania. It was a facade beam, so an edge beam. Strand cover didn't end up being as much as it was supposed to be, paired with just chlorides getting in there due to water leakage and not a good waterproofing membrane that led to the collapse of this beam. A little bit closer to home in Cuyahoga County in 1989, a fascia girder collapse occurred following significant spalling of the cover of the pre-stressing strands in, again, a fascia girder. So you can see the picture on the left is showing actually a bunch of spalling cover that had happened prior to the collapse of that girder. Luckily, these are not the kinds of things that we see commonly. Really, the issues that we're more used to seeing is we'll see leakage through the longitudinal joints or runoff along the fascia girders that would result in localized and more minor corrosion issues. But over time, this can cause eventually needing replacement or significant repair measures that would need to take place that would lessen the length of the life of the bridge. And so this project is really trying to look at how can we slow down the effects of this corrosion and to give the bridges a little bit of a longer lifespan before replacement would need to happen. In terms of the objectives and the approach that we followed for this project, the objectives were to identify cost-effective, proactive, best maintenance practices to lessen, delay, or slow the corrosion after the onset of corrosion of pre-stressing strands in pre-stressed box beam girders, to demonstrate proposed maintenance practices using case study bridges, and to assess the effectiveness of each method to minimize corrosive effects. And then really the main deliverable of all of this was to develop a matrix of possible repair and maintenance practices for use by county engineers. So these were our primary tasks for the project, to compile a representative Ohio box beam bridge inventory. So we had an understanding of what's the state of box beam bridges in Ohio, and getting a sort of a representative collection of these bridges. To do a literature review, understanding current practice and potential strategies that we could employ. To do field investigations of candidate bridges. So we were implementing and monitoring certain maintenance techniques on candidate bridges. So we first selected the appropriate bridges to do these techniques, and then implemented and monitored them over time throughout the project. And then again, the main deliverable being the maintenance and repair matrix that we developed. In terms of looking into the bridge inventory, so at the time of when we first started this project and using the inventory we were given, there were about 7,500 pre-stressed box beam bridges in Ohio. Using the condition ratings that ODOT Bridge Inspection Manual uses, we were trying to sort of understand where did a lot of them fall in terms of their, a rating of 0 to 9. And we tried to focus really more on ratings of 4 or 5 or even higher than that, those that sort of fell at the cusp of being considered poor or fair, and then higher than that. We felt that if you go to something much below that, you're at the point where there are kind of minimal strategies that you could employ other than just full replacement of the girder. So this is showing the bridges that we are aware of from the inventory with ratings of 3 and 4, and most of these are bridges with ratings of 4. We selected, you can sort of see there are sort of areas where these sorts of bridges are commonly being used. Northeast Ohio, Southwest Ohio, and then another little grouping in the northwestern part of Ohio. And so we selected 6 bridges from each of these areas, Warren County, Lake County, and Defiance County, we did site visits and looked at, the structural information on the bridges, photos, inspection reports, their ratings, summary of the damage, to get a good understanding of really where the problems lie. We did a survey to understand current practice, and we surveyed basically 10 county engineers from around Ohio regarding their current and past experiences that they've had with this corrosion damage to pre-stressed box beam girders. We first asked just a generic, what is there to rank the prevalence of the issue in their county, 1 being a non-issue, 5 being a severe issue, and the average ended up at a 4.3, noting that this is a pretty significant problem that they would like help to address. 80% of the people that filled out the survey noted that the fascia girders were the first of what showed signs of deterioration. We asked them to list out different maintenance methods that they've conducted. And so you'll see that some of these in this table are repetitive because the darker line is distinguishing different counties and their responses. So the first 3 are one county's response, the next 2 are another's. So you'll see some redundant responses, but we asked them to rank from 1, not at all effective, to 5, very effective, the different methods that they've used. It seems, common techniques are use of waterproofing membrane, use of drip strips and edges or drip edges, and chip sealing. These were common maintenance methods. We also asked about repair methods and their perceived effectiveness, and it seemed that many do not actually repair, they will instead replace. And methods like patching were mentioned multiple times, generally found to be pretty ineffective of a repair method. So we accumulated all this information in an attempt to, well, firstly it informed how we would create that matrix at the end, but also helped us to try to come up with different procedures that we can test out and evaluate over the course of the 3 to 4 year project that we had. So we focused on 4 implementation procedures. We couldn't do all of them. It's too much to capture every single possible procedure. And so we focused on 4 approaches that maybe aren't done as much, but to see how effective they could be. One being longitudinal joint maintenance. We had 2 bridges in Fayette County where we performed this work, and we'll explain the details of each of these. Cathodic protection using a decommissioned bridge from Defiance County. Polyurea application, we applied this to 2 bridges in Fairfield and 1 in Fayette County. And then we did some chip sealing, just observing the process and monitoring it briefly for a bridge in Fairfield County. We're going to take time today to talk about the first 3 and the procedures that we followed for that. So I've mentioned now that it's been a reoccurring thing that longitudinal joints are where a lot of leakage happens, and that is primarily due to shear key cracking. So I mentioned that shear keys are present between each of those adjacent box beams, and cracking can occur. This can happen due to a thermal gradient or due to differential movement of the adjacent box girders relative to each other. This is the result. These graphs are not our own, but from this NCHRP project, the report came out in 2023, where they were looking at this effect of thermal gradient and causing cracking of the shear keys. So the image on the left is showing as you have a girder depth, as you go down in the depth of the girder, it shows the different thermal gradients that were observed just from day-to-day heating and cooling, the sun exposure to the girder. We're not talking about fire temperatures, we're talking about just sort of the day-to-day temperature fluctuations. So in the top 4 inches of the girder, you could see a fluctuation of, 50 degrees that can occur. And so the image on the right is showing camber of these girders. And so due to just a 24-hour time frame, essentially warming up due to the sun exposure and then cooling down at nighttime, and showing how the girders move. And you can see there's some differential camber between the different girders. So we wanted to address this issue and through a maintenance procedure. The detail on the far left is showing the typical ODOT shear key detail. So it's typically you would grout it with the cementitious grout at the geometry and the depths that are shown in the image to the left. And so what we wanted to do in this maintenance is to acknowledging the fact that there is a lot of cracking that happens and that there's a lot of thermal stresses that are induced, particularly at the top, is to install a flexible joint sealant at the top so that it can accommodate differential movements that might happen and the stresses that could be present there. And so that is what we observed and had done again on 2 bridges as part of this maintenance procedure. So this involved actually grinding the shear key. We did not grind the full 3-inch depth that's shown in the previous slide. In this case, we just did the top 1.5 inches of that. This was done by a subcontractor. Essentially, they attempted first with a sandblaster. That did not work. They used a partner saw and an air chisel, which was ultimately what they ended up doing. But it was a tedious process. It took their crew a full day, about 10 hours, to grind out the keys, which ended up being a rate of about 32 to 42 linear feet per hour it took to grind out the shear key. Use of appropriate equipment would speed up the process. Using some kind of walk behind crack rotting machine would have been probably a quicker and easier option here. Then they installed a sealant, so a hot applied single component polymeric joint sealant. It's called Seal Tight. This could be done at about twice the rate of the grinding process. And we wanted to monitor its effectiveness. So it's not just looking at it being done, what's the cost associated and the time and the equipment and all, but was this an effective means of repair? And so what we did is we flooded the bridge surface. We did it 3 times. We did it after the top was ground out or milled. We did it and then before the sealant was in place. Then we did it after the sealant was installed. And then we came back 18 months later and flooded it again just to see if we noticed any differences that would have happened after some time had passed. We had approximately 500 gallons of water that we would just walk behind the truck as it slowly passed and poured the water in 2 passes. So we went across twice. We would be under there while this was happening, observing the water that would be coming through or not coming through. And then we'd go back again hours later as well in case it took some time for water to make its way through. And we wanted to make sure that we were also checking on it a little bit later on as well. So this was White Oak Road Bridge. That was one of the 2 bridges that we looked at. This was before any of the flooding took place at all. So this is the status of it prior to the maintenance. You can see some existing stalactites and some efflorescence and staining due to clearly there has been water leaking through in the past. But it's all pretty dry. There wasn't any real active leaks. Once we flooded it, so this was again once the shear key, the top 1.5 inches had been ground out and we had flooded it before we put in the joint sealant, we were seeing very active water coming through essentially immediately. While the trucks were still above our heads, there was this water pouring through. You can see maybe in the arrow in the picture to the left that we had active dripping of water coming through. This video, hopefully it's not buffering too much for you. If not, it's not super critical to it, but you would hopefully be able to see some of the active leaking. Now, a lot of the sound you would be hearing here, if you're able to hear the sound, that is because some of the water is running over the sides of the girders. So not all that sound is just leaking through the longitudinal joints. But it was really a lot of water coming through, like an astounding amount of water really coming through, leaking through those joints. In every single joint, and in some areas more than others along the length, but consistently in large portions along the length of the bridge. I'm only showing you here the results of the White Oak one. There was another bridge and really the same exact findings that I'm showing you from this one were found in the other as well. A week later, we went back after they'd sealed up the joints. This is what it looked like after. So you can see there, when we came the following week, we still had not flooded it yet at this point. So this is kind of, we just got to the site, we're looking at it. There's definitely some water there, wet spots. It had rained pretty much the week between when we ground and did the sealant. And there's the potential for, some water to have leaked through still from the flooding that we did previously. But no super active leaking going on. This again, hopefully the video is not buffering too badly for you. This is after we installed the joint. And really, I don't know if you could tell the difference from the small picture, but moisture, but no active leaking like we saw before, except in one area. There was one portion near one end where there was a lot of water coming through. But in no other areas where we had applied the sealant. So potentially there was it wasn't applied as well in one area as in the others, but otherwise it really cut down on the leaking almost entirely by adding that joint sealant. We did come back 18 months later and we saw the old signs of leakage, but there were no new active leaks despite extensive rain having happened. This was May, so there was lots of rain going on and there was no active leaking, no signs of recent water that had made its way through. Now, it should be noted that, they had put on a waterproofing membrane, they had reapplied the roofing surface. So that also is providing resistance here. When we did the flooding, we have kind of a belt and suspenders approach going on. We've prevented the cracking in the shear key, but we also now have this waterproofing and the surface itself to keep the water out as well. But it seems to have done a good job and been effective in keeping water out of those longitudinal joints, which is one of our big issues that we see with these box beam girders. At this point, we can take any questions that you have so far on what I just presented, and then we're going to switch over to my colleague, Dr. Steiner, to present on the cathodic protection piece.
No questions so far. I'm sure they're still thinking of them. So I will go ahead and get things switched over to our other presenter.
Hey, give me a second. Let me make sure everyone can see my screen.
Sure.
I think I just told it to share. There we go. And then, yep, there we go. So hi, everyone. I'm Matt Steiner. I'm an associate professor in materials science. Yeah.
I'm sorry. I'm not seeing your screen, so I'm assuming everyone else isn't. Yeah.
It's in the audience view for me, so I don't know why that would be.
Yeah, I'm just still seeing the white box.
I have, you know what? I have two options. Let me try.
Oh, okay. It says someone else said that they can see your screen, so I guess you're good. It just must be my computer.
I'll go back to the other.
You're good.
If
As long as everyone else can see you, that's fine. Thanks.
I can see it as well, Matt. So I think
yeah, okay, good. So sorry, everyone. Yeah, I'm Matt Steiner, associate professor of materials science here at the University of Cincinnati, and I'm going to talk about the cathodic protection trials that we did on a girder from a decommissioned beam from Defiance County. This was a rating of 4, so it just entered that PORA territory, and is broken to get to us. It came in 3 different sections, about 16 to 20 foot spans we're dealing with. And critically, when you look at the pictures here, what you're seeing facing you is actually the bottom of the beam when it was installed on the bridge. For safety reasons, we had to turn it 90 degrees on its side. So when you're seeing this front face that would look like the fascia, it's actually as if you were looking up from the bottom here, just to give you an orientation. And just a quick overview of cathodic protection and how it works in corrosion in these bridges. So the top left picture, you have steel and concrete. This is the problem we're dealing with. And critical to understanding any corrosion process is it's a circuit. You have an anode, which is the thing that's going to dissolve. That's where your rust is going to form. Cathode, which is a material relevant to it. And there's 2 important bridges between these materials that's necessary for corrosion to proceed. You have a metallic bridge, which in this case will be the steel itself, that's able to transport electrons from the cathode to the anode. And equally important, charge would build up in that case, and it eventually would self-limit. You need an ionic current through the concrete. If you do electroplating, this would be the liquid medium. But the ions are going to transport through the concrete back from the anode where they're dissolving out to the cathode, and this is necessary to kind of propagate that corrosion. The idea of a cathodic protection is you put a sacrificial anode. So instead of the steel corroding the steel, aided by the chlorine atoms in the concrete, we're going to put a sacrificial anode in contact with the concrete. It has to be in physical contact. And the circuit here is going to be 2 parts. You're going to have a wire that runs from the cathode to the anode, and it's very important. You have to provide a way for the electrons to leave the cathode, and this is how we're protecting the steel, is that whatever the electrons are going to is going to corrode. So we provide the electrons away off the steel, and then the chlorine atoms are going to be still conducting current through the concrete, but from the anode to the cathode now, and actively protecting the steel. So there's 2 components. We need our anode in direct contact with the girder, and we need a wire connecting to the steel. And one of the big questions that is hard to answer without actually taking one of these things apart and testing it is how connected the steel is within the girder. So we have multiple strands and stirrups, and there's really no guarantee that each of these makes electrical connectivity with each other. And that's important because if they weren't connected, you would have to individually attach each one of these. You'd have to have an electrical lead attached to each one to employ the cathodic protection, which would of course make it a much more invasive procedure. You're having to go in and attach each one of these through the concrete. And one of the major findings we got, thankfully right off the bat, is that each of the strands in these sections we were testing, so even within these 16 to 20 foot strands, is electrically connected to the other strands in the section, presumably through the stirrups, which cross all of them inside. So in order to employ cathodic protection to a box beam bridge, assumably you actually only need to make 1 point of connection per, every so much distance, and the steel within that girder is all electrically connected. So you're going to protect all of the steel off 1 point of contact, which is great. We tried 2 different cathodic protection products, both provide by vector corrosion. The first one I'm going to talk about is their older product. The second one is a newer product, which is now commercially available. It was in development when we were testing it. And the idea here is the first one is just a zinc sheet. It's applied as you would apply tape to something like masking tape. There's a special adhesive behind it. So you cut it and you roll it out and you literally stick it or paste it onto the girder surface. That's going to basically complete one side of that circuit potential. So now that is through the concrete, making the ionic connection. And then you attach wires to it just simply via welding to complete that connection. In our case, we just attached them to the free strands on the outside of the girders, which had been broken apart. So that's the application here. It really is just a process of, you can see in the far left bottom, effectively just pasting it on and then sealing up the edges, because critically you don't want water sitting under here and delaminating it. Especially, we have this, vertically mounted, but this would be on the underside of the girder in an actual application. But you apply the epoxy, you put the metal wire leads on it, and that's the installation process. It was fairly quick and easy. You can see a couple small drill holes where we mechanically mounted it as well, but not going very deep at all into the surface there. The other product, instead of pasting on the zinc metal and having the zinc metal exposed on the outside, is more similar to if you had pre-installed cathodic protection, say in a large infrastructure product. Typically, if you have zinc anodes embedded in the concrete, what this is we're going to extend the girder effectively by putting zinc anodes in a grout, which is going to act like that concrete and still conduct the ions. But everything's basically contained in a strip here. So you apply the grout, you mechanically mount it to the surface of the girder, attach a wire again to the steel in the girder somehow, and that's the installation setup. Relatively quick and easy, and really mimics the kind of pre-installed cathodic protection you can see in some large infrastructure products. So those are the two things we mounted. We tested, we had 3 girders. We kept 1 as a control, 2 were cathodically protected. You can see here, each one of them was protected on one side by these strips, on the other side by the zinc sheets. And we set up, you can see underneath there, the little doghouse and all these wires running around. We set up a monitoring system so we could evaluate how well the cathodic protection was working, as well as some in situ resistance monitoring I'll talk about next. But the installation is really, it's a surface mounting, and then at some point you need to connect it to the steel. So that would be, again, drilling to the steel and grouting behind it afterwards. And the monitoring we're going to talk about, we're going out periodically and salting these beams. Matter of fact, salting them probably more than they would see in normal service to try and accelerate things as much as possible. And we did this monitoring through a number of seasons, which posed their own challenges, the heat and the cold and the computers. But we started in June 2023 and went through August 2025. So we captured winters and summers in here, and you'll be able to see some of those temperature differences in the next slide. So the way we can tell the cathodic protection is working right off the bat is it is an electrical circuit. So what I'm showing here on this slide, on the x-axis is your time. So these are dates by month. So you can match those up to the times of the year, and you guys know the weather here as well as we do. So we started in the summer, and this spans all the way to the May of 2025. On the y-axis, you have the current, and this is the current in that cathodic protection. And the way to think about the current is these are the electrons that we're getting from the steel that are going to the zinc that are not corroding the steel. So every electron that we're measuring here would have corroded the steel. And what you're seeing at the first 4 months or so, this is very much expected because we had so much exposed steel, is a passivation of all those strands that had been cracked open on the sides. But by around, October, November of that first year, we had reached a bit of a steady state, which means that the system is just working. Everything's, this is comparable if we hadn't had a sectioned girder, what we've been looking at kind of as our starting point. And the real takeaway here is you do see fluctuations, and these are based on the times of year. We're going to see the protection current is lower during the winter because the ions move through the concrete slower. So there's going to be less active corrosion at that time, even though we're applying more salt. And then during the summers, when things heat up, things move a little bit faster. So you're seeing around the May, June, July 24, you're seeing the current increase. Then it decreases again for the next winter. And unfortunately, we stopped in May, but you're starting to see the uptick again. So what we're getting here is this fluctuating baseline of cathodic protection. And that really just means that everything's working as intended. Everything we measure here is corrosion that would have happened on the strands that we're protecting. You do see some pretty active deterioration of these zinc sheets. This, again, it means it's working. This is corrosion that would have occurred to the steel inside the girder if it was not happening to the zinc. Top left, you see as installed, followed by, after a good chunk of a year and again. And within the time period we looked at here, the zinc was starting to crack and peel apart. This is a little unfair to the product simply because we have, in this case, because of the open ends, we have a lot of exposed steel here. So this is kind of accelerated timescales. This is not what you necessarily expect to see in the same time if you had applied this to a system that needed a little bit of help, as opposed to just being split open with all that exposed steel. But it gives you an idea of why the strip method might actually might work a little bit better. Eventually, if this zinc broke apart and you lost the electrical connection, it would stop the cathodic protection. That wire going to the steel is as important as the zinc being in contact with the concrete. So those were some of our major findings. Again, the difference between the strips and the sheets was relatively minimal in the previous slide, and accounted for simply by the amount of zinc that we applied relative to the size of the concrete girders. So everything worked as intended in this application with singular connections to the steel. So we were protecting all of the steel off a single connection, which is really important. And since we had connected everything for all of these monitoring systems for the cathodic protection and gone through that, we also thought we'd test whether we could actually make some in situ monitoring measurements using resistance on the prestressed strands to see if we could actually figure out when they were corroding and if they were going to break in that time period. So the idea here is very simple. We're measuring what relative to a reference, how much electrical resistance the strand has. The more corroded it is, assuming the resistance will go up. And we kind of tested this in the lab to give ourselves a baseline to understand, what types of losses would be necessary for this type of measurement. We did this simply by taking a strand non-corroded and mechanically cutting it. So what you're seeing here is, cut number 1 is relatively small. We didn't go through any of the wires composing the strands completely. Cut number 2, we started to completely separate a couple wires. But really, by about the time we lost about 30% of the strand cross section, which is cut number 3, you're seeing the difference between those red data points and the blue data points. And that's a measurable difference. So what we're expecting with the resistance is when we lose about 30% of the corrosion cross section of the strand, we should hopefully be able to see that and know that the strand is undergoing, corrosion that might eventually completely separate it mechanically. So this is mechanical. Before we set up the monitoring system, it gave us some confidence that we would be able to make a measurement. What we did is we set this up on 6 different strands that were embedded in the girder. So we're putting connections on both sides of them where the metal is free. A lot of prep work to do that. But we chose in each of these are fully embedded strands. So these are strands that have not had the concrete spall off next to them. But we intentionally chose some that were both completely embedded and away from where the damage on that box beam was versus some that were very close to their neighboring strands were partially exposed at some point. Hoping that we would be able to capture one of these things actually corroding in situ. We also chose, of course, 3 on one of the cathodically protected versus 3 on the control. What you will see is that, unfortunately, in the 1.5 to 2 years that we were monitoring, none of them experienced significant corrosion. But we did take a 7th strand and place it outside with the box beams, so exact same temperature conditions. You can guess which one it is. It's the dark blue data here. strand number 7. This is a loose strand that was just sitting out and exposed to the environment and corroding, and you definitely are able to pick up a response here. So you're seeing within about 200 days, we're up to a loss that in the mechanical tests would equate to about like a 30% cross-sectional loss. So it's beginning to come apart. And then actually from that point, it rapidly accelerated. And unfortunately, somebody in maintenance accidentally cut one of the wires out in the field here. So we lost the data before it completely disconnected. That would head up to infinity at that moment. But you can see kind of the time span if you just had a strand completely exposed, that it's going to corrode just the point of going in 250 days. And the 6 strands that we were monitoring are all the other colors on this plot, and you can see that they all stayed pretty close to home, which just means that we weren't getting any real active corrosion, even though we were salting these beams. We had picked all of these as intentionally embedded, so this is not much of a surprise. But it did give us some really critical data since we were running this experiment over would this be a viable technique to use to try and determine if strands are disconnected or not. Could I make a resistivity measurement across the strand and guess what the state was? And what we figured out is you can definitely tell when a strand is significantly damaged here. And there's some scatter due to a lot of this is post-process data. We've had to deal with temperature. And the real finding we had is the scatter due to the temperature is large enough that if you weren't doing a continuous monitoring scheme over a period of years, it'd be very difficult to tell just if I made a resistivity measurement on a strand, whether it's fully connected or not. Rather, how much corrosion damage had occurred. It could be due to temperature variations. So this is technique, while interesting academically, as an ad hoc measurement to see, is the strand corroded or not, you're not going to get much of a response. And actually, because the steel, through our other finding, because the steel is all interconnected, if one of the strands was completely corroded, it wouldn't actually, it would still give you a measurement. You'd still be able to run current from one end of the beam to the other. It would just pass through the stirrups into another strand and then back to that strand past wherever the corrosion was. So this, negative findings are also important as to, what we can and can't do in terms of monitoring systems here. And I believe that with that, I pass it back to Rachel, if there aren't any questions.
We do have one question for you.
Okay.
It says, as you know, ODOT has a general permit from Ohio EPA related to bridge maintenance wastewater. Did the project look into benefits or limitations that can result from implementing the maintenance practices identified on this project? Or does it provide recommendations that could be considered in the next permit renewal?
This is a much better question for Rachel, because I think it relates to the project as a whole. Rachel?
Yeah, sorry. Can you repeat the initial part of it?
Sure. It says, as you know, ODOT has a general permit from Ohio EPA related to bridge maintenance wastewater. Did the project look into benefits or limitations that can result from implementing the maintenance practices identified in this project? Or, you want me to keep going?
Yeah, go ahead. For completeness, sorry.
Or does it provide recommendations that could be considered in the next permit renewal?
So as far as like waterways and the implications of that on our project, so the next one that I'm going to talk about, for example, was an issue where we had to consider the potential of, if you're going to be applying this surface, this material, is there potentially could get into the waterways, and do we have issues with that? We reached out to get guidance on ways that you can, and I've included this in the report, ways to mitigate issues with getting any kind of chemicals into the water as you're doing these processes. But we didn't look anything particular into like the permitting process. So I think that was a little bit beyond our scope, if I'm understanding the question correctly. But we did, as part of the matrix, we tried to include limitations. So a limitation of the procedure I'm about to mention is that you need to be careful about making sure that you're not getting this material into the water. It's not a highly toxic material or anything, but just to be careful in that way. I don't know if that
No.
totally addressed the question. Feel free to follow up with if you'd like some more information or to discuss it further.
Thanks. And there are no other questions at this time.
Okay. All right. Well, thank you very much. We've addressed a way to keep water out of the longitudinal joints through those shear key and installing a flexible sealant. We've looked at means of arresting corrosion through cathodic protection. And now the last method that we looked into in any kind of great detail or more detail was addressing the issue of the fascia girders and the deterioration of the fascia girders. So the procedure that we followed here was to apply a polyurea to the fascia girder. We did this on 2 bridges in Fairfield County and 1 in Fayette County that had fairly significant deterioration of that fascia girder. This polyurea, or you'll see another term for a similar product, polyaspartic, it's a polymer compound created by mixing a resin with a catalyst. We specifically used Creative Materials, that company's product, but there are other products out there that do something similar. It's a pretty elastic, painted on material that really keeps things locked in. It doesn't, the concrete's not going to be just falling off. You have good adhesion, and it stays intact for a really pretty long period of time, it seems. So these were the bridges that we looked at, some pictures here. I was present for the one on the left. It was just a 9 square foot area that was pretty heavily deteriorated, and I was present for the installation of that one, so I'm going to show you a little bit about that. Before we even did this though, this is not the first time that this product has been used on an ODOT project. So this was a report from 2021, a project where they were looking at, it ended up being in District 6, but piers for overpass bridges. You have cars driving under that kick up all that, those salts and chemicals that can deteriorate piers. And so it was looking at applying these different sorts of products to piers. And this coating specifically was applied in October of 2018, and it was evaluated again in February 2024. One of our members of our technical committee that was in the area stopped by a few of these piers and took pictures, and these are pictures so from basically 5.5 years after it was first applied. So we wanted to make sure that things were going okay in the long term for the product before we even attempted to try to apply it to our project. And so overall, the adhesion to the substrate was very good. There wasn't any peeling or flaking that was observed. You will see in the picture to the left that there's rust bleed through the coating, and that appears to be a continuous process. Essentially, they did not do any real like prepping of the steel. They didn't try to arrest the corrosion in any kind of way. They just sealed it up. And so the corrosion, the rusting that's occurring in there is going to continue to happen a bit. And that's where you're seeing that rusting bleeding through. But overall, the products seem to do a good job of locking in everything and having good adhesion. So we applied this product. It's a water chasing primer. It actually really likes if the surface is initially wet. You just have to clean off the surface, remove excess concrete, just like use a pressure washer or air to clean the surface. No special surface prep required. You can apply a top coat that with or without a pigment, and there are multiple coats that you can use. And you can also do it with a patch or without a patch. So here is actually the finished product of the one that we had worked on. They did not opt to bother with applying a concrete patch. This was all just applied just directly to the exposed concrete remove the bad concrete and then get to some good concrete and applied it then. This company offered a rust converter product that was used to arrest this. In theory, it arrests steel corrosion. So it's actually painted onto the steel, and the idea being that bleeding through that you saw previously could be slowed down because of this product that will stop that. And then it's applied easily with rollers and with paint brushes. So it's pretty simple to do. So this was done just again on that one little area. There were actually 3 people on the crew, probably only really needed 2 for such a small area, but 3 were on the project, 1 mixing the compound and the others applying the the polyurea. The challenges with this product are that it has a short pot life. So it said 10 to 30 minute range on some of the coatings. It would start to get pretty tough to be able to paint. And for some of them, honestly, it happened closer to 10 minutes. So you have to mix really small amounts and work kind of quickly. And so that's a challenge, not so much a challenge in this small area, but if you were going to larger areas, you'd have to do lots of small mixes before the material would set up. And then curing time was an issue too. The curing time for one of these coatings took over 2 hours actually. And when you're just doing a small area like this and just focusing on this, you have to wait for that to cure before you can do the next coating. That's a lot of time just sitting around. Now, if you're applying it to multiple areas across a bridge, you could presumably be working in this area and move to another one. By the time you're back, it could have cured and you can move on to the next process. But there is some downtime definitely associated with waiting for the cure time. This was done in 2 counties. The other county that did this work as well said the process was simple and had the same issues, essentially short pot life, and that the curing time was just a little bit slow. We went back 8 months later. This is showing the that area, just looking at it later. There's an area pointed to on the left where there seems to be a little bit of delamination there. So maybe we didn't clean off the surface good enough to get to sound enough concrete, or we did only apply, we didn't apply a second coat of one of the primers because of the time issue. We actually ran out of time in the day. And so, you know, having another coat may have helped things to prevent that. But overall, it did a pretty good job so far in locking things in and protecting the surface and not making the concrete spalling, you know, become a bigger problem with time. Okay, so those were the methods that we employed and we looked into in more detail. And so really the goal of this project, and what I hope you'll get some value from in the report that will be available, is the maintenance and repair matrix that we generated. This was meant to assist in decision making. What we tried to do is to link it to observed damage that you might see certain damage, and so it would give you then, okay, if you see this, what methods are potentially good methods that could be used. And then we grouped them into 3 main categories: a maintenance category, a routine repair category, and then a more substantive repair category. I can't possibly go through these in any kind of great detail today, but you'll have access to it if you'd like to take a look, and hopefully it'll be helpful. We kind of categorized the damage as 6 different types, ranging from 1 being joint leakage with no efflorescence or any corrosion evidence, to 6 being exposed strand with extensive section loss of the strand. And so with each of these, this one's showing just a few of the ones for maintenance procedures. And with each of these, we would say for each procedure what damage type would work, that 1 through 6 that I just showed you on the previous slide. What bridge rating range would be helpful, that this would provide value if it was within that range and you were doing these processes while it was under that rating. The description of the work, an estimated unit cost. We did materials and not labor as much as we could, because sometimes the work is being done by the county, sometimes it's being subbed out, and we didn't know how labor would be included. Any equipment requirements, and then any material requirements. And then here's that consideration or limitations. So the mention of, you know, if you're doing work over waterways, and maybe you need to be concerned about certain work being done over the waterway. And so noting those sorts of instances where that might be something that you have to look into and consider. And then photos of either the work being done or the repair completed. This is just showing you routine repair procedures, just a few. So examples like chip sealing, crack sealing of asphalt, concrete patching. And then more substantive. Replacing the deck, or you need to remove a lot of concrete and you decide to use embedded anodes, a form of cathodic protection that we did not use on this project. Okay, and so this is the matrix that we developed that include these different kinds of information, again, to try to be somewhat comprehensive in terms of the options that you have for dealing with this corrosion issue on box beam girders. In terms of conclusions and recommendations, General conclusions, we found that the corrosion-related issues really occur primarily in the fascia beam and the longitudinal joints. Many county engineers have kind of abandoned maintenance procedures in favor of repair or replacement, kind of wait until the problem just becomes so big that you have to replace it. But hoping with this matrix, there might be some opportunities to be a little more proactive and take measures earlier on. We feel that proactive measures early on in the initial bridge design or early stages of the lifespan of the bridge can increase its service life. With the longitudinal joint maintenance, we found that use of a flexible joint sealant in the top 1.5 inches of the joint significantly decreased the active water leakage through the shear keys. The process actually of grinding out the shear keys was time consuming and expensive, but it's expected to be more efficient with practice and the use of proper equipment, such as a walk behind crack routing machine. Cathodic protection, the case study beams were found to have their internal steel components all electrically connected, which really eases installation because it provides the need for a lot less connection points back to your strand. Cathodic protection can be applied at the girder surface and then and connected to protect all the steel in the existing girders with those minimally invasive procedures. And the addition, this is an option, is that you could add electrical leads to future girder designs prior to casting the concrete to make the cathodic protection installation easier and non-invasive. Thinking proactively, maybe eventually I would want to use cathodic protection. You could implement some things on the front end so that it's just a little easier. You don't have to do as much drilling and accessing your steel later on. Resistivity was proven to be an effective means of measuring significant corrosion, but maybe on the application side, it's more of an academic exercise potentially. And both the sheets and the strips were easy to apply. The sheets have the benefit of visually showing the corrosion, but may delaminate from the concrete beam over time. The strips are more physically secure, but both appeared to be equally effective at mitigating corrosion, at least throughout the length of the study. We actually extended the project a year, hoping to get a little more data from the corrosion protection, the cathodic protection work. And I guess the good news is that we didn't see a lot in that it would seem to have been working. It's hard with a 3-year project to be accelerating corrosion and to be seeing huge changes in corrosion. Sometimes it happens quickly, sometimes it happens more gradually. With the polyurea, the fascia beam's exposed vertical surface should be protected from water runoff, and the polyurea can be an effective means to provide this protection. The application process was straightforward, but the cure times were time-consuming, and then the pot life made it challenging, requiring mixing of batches in small quantities. Now, in terms of implementation, I can't go through all of these individual methods and implementation, but what we found as we were working on this project is that we kept going to, how could we have made this easier at the beginning in the design phase? That could have been a little, again, proactive and make it so that we maybe don't see these kinds of issues until much later on in the life of the bridge. So while it wasn't a scope of the project, we kind of found ourselves going towards what sorts of things can we do in the fabrication of the girder itself. If these maintenance procedures are sometimes a little bit challenging to do, time-consuming, or a bit of a pain at times, how can we do it maybe earlier on, initially, so we don't have to deal with that later on? So, for example, this is again the idea of the longitudinal joints, and the image on the far left again is that shear key detail that we're used to seeing. But from that NCHRP report are these images B, C, and D are proposed different shear keys that they found to be more effective. Ones that have a larger area, bond area, more grout, they found those wouldn't crack as much. Or moving the shear key down to more of the mid-depth, they found that wouldn't lead as much cracking. Or if you want to do the approach that we did on this project, installing a flexible joint sealant like what you see on the far right, that can be done initially, right? So you don't have to go through the grinding out process and then installing the flexible joint sealant. Why not just do that initially as part of the installation process of the bridge? Chamfered drip edges or installing a sealant bead. So we're aware that this was something that has been done at ODOT before, and it kind of became out of standard practice. And to be honest, we don't totally know the steps behind that. If there's concerns about these drip edges and the kind of triangular nature of them, there are semicircle options available. And then if there's concerns about sort of creating this strip that is a removal of material in that area, another option that would involve not having to insert a strip that you would remove, but to just apply a sealant bead. So apply a sealant material where this strip is currently being shown as applied to the surface, and that would do the job of acting as a drip strip to get that, or drip edge to get that water off. And it's not then cutting into the concrete. We've said a number of times, fascia girders are really your primary issue, and especially the vertical face and right below on that, what we think the first 18 inches or so should be protected. So using that polyurea product or a silane or something that can protect the surface, and applying that earlier on, not waiting until it has already started to become a problem before doing that. Now, the details of this would need to be worked out, but the idea of this electrical connectivity for cathodic protection, and the fact that if you can ensure connectivity of your girder, that you have to do less of sort of drilling in and connecting to the strands later on. And so thinking proactively about maybe you'd want to implement cathodic protection, providing, like, for example, a transverse bar that would just be attached. Now, what we found from this work, as Matthew said, was that we found that it is connected. It was connected for the girders that we saw. If you had a second layer of strand, though, that may not be part of the circuit, part of the connection. And so maybe you need another bar that would be connected to the second layer potentially. This would need to be worked out, obviously, with the precast producer, and work through the details of if this were to become a typical ODOT detail or something. But there's the potential here, or the idea we wanted to put in people's minds, that if you can put some sort of strand bar that can connect to the strands, maybe on each end of the beam, that you can ensure even better this electrical connectivity. So you just don't have to drill in as many places later on to try to make sure that you have good connectivity amongst all of your strands. And that is really what we have to present to you. So I just want to do quickly some acknowledgements. So the two names that are highlighted, Richard Miller and Neil Anderson, they were the other PIs on the project. So we acknowledge their help, and huge help and work on this project. Other members of the UC team, another faculty member, Joe Corcoran, and a number of grad students and undergrads who have helped along the way. A number of county engineers and folks from different counties that either gave us tours of their bridges or let us use their bridges for maintenance, or their crews to do some of those maintenance procedures. And then some folks from Vector Corrosion and Creative Materials that acted as consultants to give us input and provided the materials to us for this work. I don't think we have a ton of time, but with the last few minutes, we're open to any questions that you may have. Thank you for your time.
Thank you, and we do have a couple of questions. The first one is, was the steel on a small area sandblasted before the polyurethia was applied?
Yes, it was. Yeah, we actually were going to do it on a third bridge, and we were trying to clean the surface well enough just to get to more sound concrete. And the issue was they kept doing it and they were getting to no sound concrete. So we didn't end up even using that because they were afraid they were going to just like go right through the web actually. But yeah, you need to clean it off well enough so you're not just going to have it, more concrete falling off.
Any thoughts on casting cathodic protection pucks into the new box beams so it is there from the beginning?
I'll take that, I guess. I mean, it's a cost issue, right? It's how we handle a lot of really major infrastructures in cities that they have cathodic protection built into them like that. It would work. It's just it's a direct cost trade-off issue as to, I think the real value of cathodic protection is especially if it's easy to install. When you get something that's beginning to run into issues, you can immediately try and arrest that and get a couple more years out of it before they continue. It might be, and Rachel could speak on this, the fascia girders, it might be worth pre-installing. It might not be something you do in every box beam girder, but the fascias being the ones that have the known issues, pre-installing cathodic protection might be very cost effective there. So that's another possibility. The great thing is if you know that they're electrically connected and you have wires are relatively cheap, right? You just need to have them sticking out somewhere and capped. You could make it so that adding the cathodic protection to the surface is not that prohibitive. If you get a girder, you're not expecting to run into issues having it. But the fascia ones, I don't know if Rachel has any thoughts, might be worth pre-installing.
Yeah, I think that's a great point.
And a wonderful place to end up. So we are right at 2:30. Thank you both for all your time on today's research results presentation webinar. And I want to thank everyone who joined us. Please look for your certificate here in the next week. And if you have any further questions, I'll send the email addresses out in the follow-up email as well. I hope everyone has a wonderful rest of their day. Thank you.
Thank you very much.